Good morning, students. In today's lesson, I'm going to guide you about the topic matrices. Here is the content of this lesson: definition and examples, need of matrices, types of matrices, transpose of a matrix, and then last, symmetric and skew symmetric matrices. Let's move forward. Yes, here it is: definition and examples. A matrix is a rectangular arrangement of numbers, alphabets, or symbols into rows and columns. This is the definition of a matrix. So what does it mean? That different type of numbers, that could be data for some observation for any event, that could be alphabets as well, it could be in symbol form as well. So when we represent all of these into rows and columns in a rectangular arrangement, so these are called matrices. Here there are three examples. If you see the first example, this is a square matrix in which the number 2 and 6 represent the first row, 8 and 1 represents the second row. So here there are two rows in this matrix, 2 and 8. If you see this position, see the position of the cursor, 2 and 8 represents the first column and 6 and 1 represents the second column. So total there are two columns within this matrix. So this is such a matrix in which two rows and two columns are there. Then if you see this second example, here there are three rows and three columns. And in this third example, 1, 2, 3 and 4. 4 rows are there, and if you see the vertical positions, total 3 vertical positions are there. So they are representing 3 columns, 4 rows and 3 columns. So this is how we usually represent a matrix. Let's move forward. The next target is, what is the need of matrices? Why this question comes in young minds. Sometimes they keep on doing the work with matrices, but the question still remains there, that what is the practical use of writing or working with the matrices? Here the answer is, matrices represent data that can be written in equations as well, and gives quick and correct approximated results in advanced mathematics, formula in physics, statistics and engineering. So while working within advanced mathematics, physics, statistics and engineering, sometimes collecting the data in matrix form, it gives quick and correct approximated results. That could be more useful as compared to the other ways to calculate the things. So that is why matrices is a useful way of calculating things or data. And I'm going to give you a practical life example as well. Sometimes students think that what is the practical use of these matrices, why we are doing this. So I hope the answer will you will get through this example. If you see this drawing, I have drawn few lines here. You can see the location A, B, C and D. This is a path from A to B. Then if you see this one, A to D, this is another path being shown from A to D, and from D to C, this is the third path. So how to relate it with the matrix? This matrix is being written here. If you see A position, C position, B and D, these are being shown to relate it with this drawing. And how this is showing the data collected from this drawing, let's consider it. If you see this A and this B, so let's take it that from point A to B, how much ways are there in reaching point B from A. So if you see the drawing, start from A, moving from here to B, there is one path or way between that which is to be crossed. So 1 is the answer. So 1 will be stored in this data. Here you can see the 1 is showing this thing. Then from A to D, how much ways are there to move from A to D? So this is A, and this path is there to reach from A to D. Again there is one way, so 1 is being written here. C to B, So see the position from C to B. C to B, firstly we are to reach point D, then from point D to A, this is another path, and then from A to B, the third path. So there are total three paths or points which are to be crossed while reaching B from C. So 3 will be stored here in the data. And the last thing C to D. So how much ways are there? Again, from C to D, you can see from the drawing, C to D only one way is there to cross. So again, one is being stored. So this is one matrix which is representing the data for this practical life example. So this is just one simple example. In advanced fields, data is being collected for different events or different things, and that data could be transformed into linear equations as well. And then definitely by solving those equations we get different results. We can solve different equations, and obviously these are being used in formulas and other stuff as well in different fields. So that is why nothing is there without purpose if we are working with the matrices within physics, maths and other fields. So there is a proper reasoning behind that. There must be some benefit of it as well. Let's move forward. The next slide shows order of matrices. Yes, this is very important to understand that what does mean by order of a matrix. Order of a matrix mean the number of rows and columns represented in a matrix. So firstly, just take the examples. 3 examples are being given here. Very simple it is. If you see this first matrix, 2, 6 represent the first row, 8, 1 represent the second row. So total 2 rows are there, as we had talked already about this. And if you see the vertical positions, 2 columns are there. So this is a matrix with order 2 cross 2. Fine. And if you see the second example, it is very clear. 3 rows and 3 columns are there. So the order of the matrix is 3 cross 3. And if you see the third example, 1, 2, 3, 4. 4 rows are there, and 1, 2, 3. 3 columns are there. So while writing the order of a matrix, the first digit represents number of rows and the second digit represents number of columns of that matrix. So this matrix is of 4 cross 3 order. Order of matrices is done. Let's move forward. The next slide is about types of matrices. Yes, understanding the types of matrices, this is very important. Let me explain you one by one. The first one is row matrix. The type of matrix in which only one row is there, it is called row matrix. Column matrix, the second one. If in any matrix, you can see the brackets are there, here only one column is there, 2, 4, 1 represents one column, no other column is there, so that type of matrix is called column matrix. The third type is square matrix. Here you can see the numbers are arranged in square form. 2, 6, 8, 1, 2 rows and 2 columns are there. 2 cross 2 matrix is there. So, and the shape is basically a square shape, so that's why it is called square matrix. And another thing that in a square matrix, the number of rows and the number of columns are equal to each other. The fourth type here is rectangular matrix. In this example, you can see, if you calculate in your mind as well, total 1, 2, 3, 4 rows are there and 3 columns are there. So what it shows, is it showing a square shape or a rectangular shape? Yes, it is rectangular shape because this side is shorter one and this side is longer one. And the other way to understand is that number of rows are more than number of columns. They are not equal, that's why it's a rectangular matrix. So yes, 4 types are done. Let's move forward and discuss the other types of matrices. Yes, the fifth one is identity matrix. There are 2 examples being shown here. You can see 1, 0, 0, 1 and then this one. This is a 2 cross 2 matrix and this is a 3 cross 3 matrix. Why we call it an identity metric? You have to see the diagonal position. Here in this matrix, in the diagonal position, only 1 is written. Fine. If you see the position of the cursor, it is showing the diagonal position. And in diagonal, only 1 is there. And above the diagonal, all zeros. Down to the diagonal, all zeros. This is the sign, or this is how you are to understand that what type of matrix it is. Similarly, if you see this one, diagonal position shows 1, above the diagonal all zeros, down to the diagonal all zeros. So this is showing again identity matrix of 3 cross 3 order. Diagonal matrix. In diagonal matrix, if you see the position of the diagonal, 5, 8 and 7 are there. These are different numbers. It's not 1. It's not the same number. Different numbers are written in diagonal position, but it's non-zero element. And above the diagonal, if you see all zeros, down to the diagonal again all zeros. So this type of matrix is called diagonal matrix. Again, I will explain that in diagonal position, non-zero numbers are written and they are not same. That's why, and again they are not to be 1 as well. If it is all 1, it will become identity matrix. And another thing is that the numbers need to be different here. They are not to be same. So this is diagonal matrix. Scalar matrix. Scalar matrix is comparatively little bit as it is like diagonal matrix, very slight differences there in diagonal and scalar matrix. Let me tell you what is that. If you see here in scalar matrix, in diagonal position, non-zero numbers are there, but the numbers are same. All 3s, it could be all 7s, or all 5s, any number other than 1, but it need to be same in the diagonal position. Above the diagonal, all zeros, down to the diagonal, all zeros. So this type of matrix is called scalar matrix. Then 8th one is upper triangular matrix. If you see this matrix, you can see non-zero numbers are, if you see the non-zero numbers, 2, 9, 1, 2, 7, 3. So if you try to see the position of the cursor, it is making a triangle, the non-zeros element starting from the diagonal and above the diagonal. So this is making a triangle above or along with the diagonal. Fine. And the numbers down to the diagonal, they are all zeros. So when triangle is being shown in the upper portion of the matrix, including the diagonal, so it is showing upper triangular matrix. And with the slight difference, lower triangular matrix, what it is? Again, opposite of it. If you see the diagonal position and down to the diagonal, it is making a triangle again, the non-zero numbers, and above the diagonal all zeros are there. So if the triangle is being shown in the lower portion of the matrix, it is lower triangular, and if in the upper portion it is showing a triangle, it is upper triangular matrix. So that is all about types of matrices. Let's move forward. What's next? Transpose of a matrix. Yes, very simple, very basic functions of matrices. The next thing is, what is the meaning of transpose of a matrix? Transpose of a matrix means to convert number of rows into number of columns, or vice versa. Vice versa, I hope you people understand it. Vice versa mean like converse of it. Whatever is being said, the opposite of it. Like converting rows into number of columns or converting columns into number of rows. Both are correct. I hope you will understand it with the examples given here. 2 examples are being shown here. The first example, this is matrix A, 2, 6, 8 and 1. You are to calculate its transpose. Firstly, the symbol, how to show transpose of a matrix, whatever the number is, alphabet is being showing the matrix. In an index, you will write T, capital T. So this is showing A transpose, symbolic position or way to represent transpose of a matrix. So as per definition, what you are to do, you will convert rows into columns. 2, 6 is the first row. So here you can see it is being written in column form. Then the second row 8 1, it is being made as the second column 8 1. And if you see the vice versa, instead of converting rows, the other ways you can write the column into rows as well. The first column is 2 8, write it in the row form 2 8. Second column is 6 1, and here you can see it is being transformed into second row. So both ways are correct. See the other example again, 3 rows and 3 columns. So just take the first row, make it the first column. 2 0 1, make it the second column. 6 2 8, make it the third column. So transpose is done. Very simple. And last slide here is about symmetric and skew symmetric matrices. The first thing is symmetric matrix. A matrix is said to be symmetric if A transpose is equal to A. This is the basic definition of a symmetric matrix. It will be understood by this example here. If A is 2 1 1 2, this is a matrix given. To calculate its transpose, as you know, that you are to convert rows into columns. Once you are converting, you have converted rows into column, it is again the same matrix. You can see this is A and this is A transpose, and there is no change in it. So when A transpose is being calculated and it is equal to A, there is no difference in A and A transpose, then such a matrix A is called a symmetric matrix. Fine. And what is skew symmetric matrix? A matrix is said to be skew symmetric. Here it is missed here. Wait, let me write it here. It's a misprinting. Skew symmetric. Yes. A matrix is said to be skew symmetric if A transpose is equal to minus A. You can see just a very slight difference here in symmetric and skew symmetric matrix. Like if A transpose is equal to A, it is symmetric. But if you have calculated transpose of a matrix and it is equal to negative of that matrix A, then that is called skew symmetric. Let's consider this example. A is a matrix, then A transpose, let's calculate it, and you know that converting rows into column, that is called transpose. So 0 3 minus 2, it is being converted into the first column. Minus 3 0 4 converted into second column. 2 minus 4 and 0 converted into third column. So this is showing the transpose of A. And if you match A and A transpose, the difference is of a negative sign. Fine. So if from transpose of this matrix, if you take negative sign common out, here it is equal to, like you can see this negative sign here, negative sign is being taken out, and what change will be there in this matrix? That all signs will be changed. Here yes, so once negative sign will be taken common out from this A transpose, you can see the inner signs will be all changed. Now minus 3 will become positive 3, positive 2 will become negative 2, here it was positive 3, it will become negative 3, negative 4 will become positive 4, and the other, like the same way, you will change the sign of the other elements as well. 0 is a neutral number, so it doesn't have any sign. A negative sign doesn't affect them, so it will be the same. So here you can see this thing is equal to minus A again. If you see this matrix, this is again the matrix A. So if this is the case that you have taken the transpose and it is equal to negative of that matrix A, it is called a skew symmetric matrix. So this is all about this last target, symmetric and skew symmetric matrices. I hope you people have understood it. And then finally, let's wrap up this lesson. What we have discussed within today's lesson, we did definition and examples, then why there is a need of matrices, what's the practical use of matrices, types of matrices, transpose, and lastly symmetric and skew symmetric matrices. I hope all of these targets are being achieved and you people have understood this lesson, and it must be useful for you people. If anything is not clear to you or any query by your side, you can ask me in the comment section. I'll be definitely helping you out, and inshallah I'll be making further videos as well. This was the introduction of the topic matrices. On daily basis inshallah I'll be uploading videos for the like I'll keep on working with the advanced topics of this mathematics, and if there are any special topics which you want me to make a video on, do share the topics with me in the comment section and I'll be definitely helping you out. Thank you so much. Take care.